Hello, class. In this video, our goal is to talk about a couple variations of the fence problem that we did last time. So our first variation that we're going to look at is this version where we're still using 120 feet of fence. We're still enclosing a rectangular region. We still want that region to be as long as possible. The only thing we've changed here is that we're now building the fence against a wall, which has the effect that instead of having to pay to fence in 4 sides, I now only have to pay to fence in 3 sides, because I don't need to fence in the side that has the wall. So like before, I've drawn you a bunch of sample fences that use 120 feet of fencing against a wall. And so if you remember that last time it turned out the best answer was a square, you might try to make this a square, in which case, since we have 120 total feet, you would make it 40 by 40, which uses the 120 feet of fencing, and that gets you an area of 1,600 square feet. But you'll already see that that's not the right answer, because if I drew, for example, this 25 by 70, which does again use 120 square feet, because 25 plus 25 plus 70 is 120, that's already bigger than the square fence. Likewise, this should be 10 by 100, not 10 by 1,000. This 10 by 100 one, that has 1,000 square feet, so that's way worse than either of these. And then, so you can look at this assortment of fences that I could choose from. Okay, so we can try and figure out what the best one's going to be. Maybe it'll be one of those, maybe it'll be a different one. But as always, I want to write down a thing to optimize and a constraint. Okay, so my thing to optimize is, again, area. And my constraint is, again, fencing. Okay. But my picture this time is a little bit different, because this time we have the wall. And so if I label this correctly, that will be x and x, and that'll be y. My area is still x times y, but what's changed, my fencing is still 120, but that's now 2x plus y. Okay, so always remember that's what you're digging up. You're digging up a thing you want to maximize and a constraint. And then the next thing we do is always to solve the constraint for one of the variables so that we can eliminate that variable from the thing to optimize. So in this case, I'm going to solve this equation for y, which is going to give me y equals 120 minus 2x. And then I'm going to plug that thing from the constraint into the thing to optimize, which is going to give me that the area is x times 120 minus 2x. Okay, again, all I did there was say, okay, I solved that y was this 120 minus 2x, so I plugged that in for y and this x times this, so I got this. And so I'll go ahead and spell that out. So that is 20x minus 2x squared. Okay, so that is my area, now written as a single variable function. Okay, and this has been our goal the whole time, because this is now a single variable function, so I can take the derivative of it. So a prime of x is 120 minus 4x. And remember, thanks to Fermat, that the maximum and minimum occur either at the endpoints or where the derivative is 0. So we'll solve for where the derivative is 0. So we'll get 4x is 120. That'll give me x is 30. What are the endpoints for x? Well, my endpoints are where x is 0. And then what's the biggest x could plausibly be? That would be 60, in which case then y is 0. So then we find ourselves calculating a of 0, a of 30, a of 60. A of 0 is 0, a of 60 is also 0. And a of 30 is 30. Let's see, a of 30 will be 30 times 60 will be 1800. Okay, so if we look at it then, our best possible fence has x equal 30 and y equal, and remember to figure out y, we go back to the spot where we solved for y. So I come back there and say, okay, so y is 60 and an area of 1800 feet squared. So if you come back and look at our picture over here, that actually is not one of the ones. That's actually better than any of the ones we wrote down before. So if I draw in another wall here, I can actually label what the right answer was, so you can compare it to the others. So this is 30, 30, 60. It was 1800 feet squared. So the closest one we had before was this one, but actually this is the best fence. That's what we just figured out. Okay, so this is our best possible fence in terms of area. Okay, so now we're going to do another variation on this fence building question. It's going to be different in a couple ways. So now we have a farmer wishing to build 2 rectangular pens, and each of those pens has to have area 2,400 feet squared. But the farmer is going to save money by building those pens side by side. In other words, one of the side lengths between the 2 rectangular pens is going to overlap. And then the question is, what's the least amount of fencing with which she can do that? So if you couldn't quite follow that from the description, here's a bunch of examples. So here, 120 times 20, that's 2,400. So this area is 2,400 and this area is 2,400, like it's supposed to be. And I've written here the total amount of fencing for you. So this uses 440 feet of fencing. So where is that 440 coming from? That's 120 plus 120 plus 120 plus 20 plus 20 plus 20 plus 20. So that is 440 feet. Likewise, if I instead make these pens 80 by 30, then it comes out to be 360 feet. If I instead make them 40 by 60, that works out to be 360 feet. Okay. Or here, if I made them 60 by 40 instead of 40 by 60, you'll see that this works out to be 180 plus 160, which is 340 feet. Notice, even though the dimensions in these two are the same, this one is way better because the side they have in common is the longer side instead of the shorter side. So that saved me 20 feet of fencing there. Okay, so we want to figure out what's the best. Is the best one of the ones we've already drawn, or is there another fence that's even better than any of the ones we've done so far? So here again, we have a thing to optimize. And we have a constraint. But notice that these things have flipped from the previous question, because now the thing I actually want to optimize is actually the fencing, because we actually say we want the least fencing. And the constraint is now the area, because the area is given to us. It has to be 2,400 feet squared. So I have to draw my general picture over here. So I'm going to make this x, 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 y, y, y. And so I want to rewrite all of this in terms of this picture. So my fencing is going to be 4x plus 3y. And my area, that's the 2400. Remember, that's the area each pen has to be, so that's just x times y. The total area would be 2x times y, but that's not what I was given. I was given the area of one pen. Okay, so this is my setup as before, where I now have, okay, here's my constraint, and here's my thing to optimize. But you have to be careful to read the question to make sure you know which of these is which. Okay. So looking at this constraint, I need to solve the constraint for one of the variables. So when I do that, I'm going to get y is 2400 divided by x. And then I'm going to plug that into my equation for the fencing. So I'm going to get fencing, which I'm going to call f, is equal to 4x plus 3 times 2400 over x. Okay, which if I write that a little bit more cleanly, this is 4x plus 7200 over x. Okay, now notice, what is this saying? This is giving me a function that expresses how much total fencing I need to use in terms of how wide I choose to make one of the fences. And so if I choose this to be, say, 20 wide, like back in this first example here, then I get that the total amount of fencing I'm going to use is going to be 4 times 20 plus 7200 over 20, which if you work out, that'll be 80 plus 360, which is in fact 440. So this 440, that is this f of 20. Likewise, this 360, that is f of 30, and this is f of 60, and so on. So this f, this is the thing whose value we want to minimize. So how do I do that? Well, I take the derivative and set it equal to 0, right, as has become a theme. So f prime of x, what is that? It is 4 minus 7,200 over x squared. Again, remember here I had to take this derivative by writing this as x to the minus 1 instead of divided by x. So 7,200 times x to the minus 1. Bring down the minus 1 to the front, and then subtract 1 from the power, which gives me this minus sign, and then that x in the denominator is now squared. Okay, and so I want to know, when is that 0? Okay, so that gives me 4x squared equals 7,200, which gives me x squared is 1,800, which gives me that x is plus or minus the square root of 1,800. Okay, which is the same thing, by the way, as saying x is plus or minus 30 times the square root of 2. Okay. By the way, the minus makes no sense because the x here is a width. So I definitely don't want the width here to be negative. Okay. So now I am meant to examine what happens at the endpoints and what happens at this point, this 30 times square root of 2 that we just found. Okay, so I have to decide, what are the endpoints? What is the smallest I could possibly make x? Well, x certainly can't be smaller than 0. And then what's the biggest I could possibly make x? Well, actually, there is no limit to how wide I can make x, because if the height is small enough, x could be arbitrarily large. So this x could be 1,000,000. My pen is super, super, super wide, but there's still some height it has to be in order for it to be 2,400 feet squared. So the maximum here is really, I'm just going to write infinity. But definitely the amount of fencing I'm using, if x is enormous, is also enormous. So I'm just going to write equals infinity. But I don't really have to think about that option, right? If my fence is enormous, then, well, that's just not going to work out well for me. Likewise, what's f of 0? Well, that corresponds to choosing these to be infinitely narrow, which means no matter how big y is, I'm still not going to get there, so I'm also going to write infinity there. Basically, the moral of the story here is these two endpoints just don't matter. The only thing that matters is actually the amount of fencing at this 30 times the square root of 2. And I can evaluate that because I have my function for f here. Namely, my function for f is right there, so this is going to be 4 times 30 times the square root of 2 plus 7,200 divided by 30 times the square root of 2. Okay, so this is going to be 120 times the square root of 2 plus 240 divided by the square root of 2. Which, if you think about it, that is actually the same thing. So this is 120 divided by the square root of 2 plus 120 times the square root of 2, which is going to be 240 times the square root of 2. So this is the least amount of fencing that we could use. And if you're curious, that amounts to about 339.4 feet of fencing. Now, that's kind of amusing, as it would happen, because we looked before at all of these, and one of the ones we just happened to guess was this 40 by 60 fence, which turned out not to be the best. But it turned out not to be the best by a very, very, very slim margin, because our better fence that we found was actually better in that it saved 0.6 feet of fencing. Now, you might ask, why is that? And the reason why that is that my x here worked out to be 30 times the square root of 2. And what is 30 times the square root of 2? Well, 30 times the square root of 2 is 42.4, so it's really quite close to where it is in this picture. Okay, so we have the best possible fence here, uses this much total fencing, and it is x equals 30 times the square root of 2. And y equals, and so we can figure out what y is. We never actually write it down, so I'll write it down for completeness sake. Y is 2,400 over 30 times the square root of 2. Okay, again, I'm going back to the very start when I solved for y in terms of x. And this is, if you like, this is 80 over the square root of 2, which is 40 times the square root of 2. So pay attention to what the question asks you. Some will ask for the dimensions, in which case you would want, okay, it's 30 times the square root of 2 by 40 times the square root of 2. Okay. And some will ask for, say, the total amount of fencing, which in this case would be 339.4. Okay. So, we'll wrap up this video there. When we pick up next time, we'll do some more examples where we'll try and maximize and minimize some other things. So we'll look at some volumes, we'll look at some distances, and so on. But, until next time, be well.